All right, good Friday morning, everyone. So we'll get started. A couple of reminders here. So one is the last lecture was an asynchronous lecture and it's recorded. The link is posted on Moodle. So if you haven't watched the lecture yourself, make sure you watch it. There's a couple important examples I went through in that lecture. It's actually a shorter video. It's less than 30 minutes, so it wouldn't take too much of your time. But make sure you watch it if you haven't done so. The second reminder is the next homework is due on Tuesday. Okay, so only about 4 days from now, or yeah, more than 4 days from now. But make sure you start working on them maybe over the weekend. Okay, and then you should make sure you get a chance to finish all the problems by Tuesday. Okay. All right. So we'll start today's lecture here. We'll still be looking at the energy conservation here today. So briefly, this is what we learned earlier, actually a lecture before last one. So conservation of mechanical energy. So if you have work just done by conservative force, um, or the work done by all other forces, other non-conservative force will cancel out each other, then that also applies. So conservation of mechanical energy then apply. So that means the potential energy plus kinetic energy should be constant, not changing. So then initial is equal to final. Okay. Um, we also learned earlier. So this would be would be in last lecture. If not, then will be the previous lecture. But we also learned that so in general, you will have both conservative force and non-conservative forces doing work at the same time. So when that happens, then the work done by non-conservative force it's equal to the change of the mechanical energy, meaning change in potential energy plus change in kinetic energy. Okay, so this is in general when you have work done by non-conservative force. Then you can start with this equation where work done by non-conservative force is equal to change in potential energy plus kinetic energy. Okay, and then we look at one example on this last time in the asynchronous lecture, and then we are going to look one more example here today. Okay, so this one, it says a 60.0 kilogram skier with an initial speed of 12.0 meters per second coasts up a 2.5 height rise as shown in this figure over here. Find her final speed at the top. Okay, given that the coefficient of friction between her skis and the snow is 0.0800, the hint given here is find the distance traveled up the incline, assuming a straight line path as shown here. So this assume this is a straight line. Forget about the curvature part at the beginning and the top of the slope over here. Okay. Now, given this guy here, the height 2.5, you should be able to calculate what's the slope here. So then this will be the hypotenuse of the right angle triangle if you put the one side over here, one side here. So then it's 90 degrees here, 35 on this angle. Okay. And then in this case, it says less friction force on the slope over here. So then there is a non-conservative force doing work, okay, as she goes up the slope, okay. So set up that the work done by this non-conservative force equal to change of the kinetic energy and plus the potential energy at the top here. So I think for this one, I will set up breakout rooms for you guys to work as groups. And then if you are in an environment you couldn't speak, you can just tell your group members for the case, okay? So let me set up, I'm going to just set up 6 rooms for you guys, okay? And then we'll take a look the solution together in a few minutes here, okay? All right, I'm opening the room now. You'll see a link to ask you to join. If you just log in, we are having a breakout discussion for this example now. So I will assign you to a room. Hello.
Hey, yeah, I had a question on this. I was
Mhm.
just curious as to Okay, so did you start with the UA plus KA sort of thing that happened with the slide? I thought when I
Mhm.
came into this, I kind of thought it was a slide in reverse, but is it a little bit different from that, or?
Right, you start with the work done by non-conservative force equal to delta U plus delta K.
Oh, okay.
Yep. All right. So I'm gonna close out the breakout room in a few in like 1 or 2 minutes. So we'll see you guys in the main room later. Okay.
Okay.
All right. So as you are all back, we will take a look at the solution together. Okay. So so she started with at the bottom of the slope over here, and then she went up the slope. That's her final where final position is. We are looking for this final speed when she went goes up the slope. Okay. So now the important thing is what happens during when she is on the slope over here. So again, it's very critical to indicate all the forces on her body over here. So you probably realize there's the weight mg, there's normal force, and then because there's friction force here, so there's friction force. Okay, she's going up, so then friction force will be pulling her down. It's against the motion. Um, so now there are three forces here. So you can see the weight, the gravitational force is a conservative force, okay, but the friction force and normal force are not. All right. So then there will be work done by the conservative force. There will be also work done by non-conservative forces. Okay. So realizing that you want to start with the work done by non-conservative force, then equals to change of kinetic energy plus change of potential energy. Okay. So then this means you are going to do kinetic energy final minus kinetic energy initial, right? Plus potential energy final minus potential energy initial. So you'll have to figure out what are these four terms individually, and then also this term. Okay. So on the left hand side, work done by the non-conservative force. Um, Now we have two non-conservative force, so then there'll be work done by friction force, there will be work done by the normal force, okay? But as we say, normal force always does zero work because it's perpendicular to the motion, or it's perpendicular to the surface, okay? And then the motion is along the surface, so then that's going to be zero, all right? So then non-conservative force is only by the friction force. So the friction force is a kinetic friction. So then that friction K should be equal to mu K times M normal force. All right. So so then for normal force here, you want to take like x along the surface and then y perpendicular to the surface there. So then you can resolve the weight into the x and y component. So x, y component here, x component there. All right. So this guy will be mg cosine theta because you are on the slope over here, and then this will be mg sine theta. Okay. So then you can see in the y direction, because the motion is along the x direction, so y direction, these two forces will cancel out. Okay, so normal force will be equal to mg cosine. That tells you this is mu k mg cosine theta. Okay, m is equal to mg cosine. All right. Now then for the work done by this force, friction force, should be equal to Fk times the displacement, okay, along this slope. So let me call the length for the slope to be L, all right? And then because F and L are in the opposite direction, so then there's a negative sign in front. So that will be equal to negative of Fk times L. Now L is this length over here. This is, let me call it H. Okay, so this is the hypotenuse L. This is H, and then this angle is 35. So then if you do sine of this angle should be equal to H over L, right? Sine of theta is going to be H over L. So then L is equal to H over sine theta. Okay, so you kind of move L to the other side and then sine to the other side as well. Okay, so then in this case, then your work done by friction force will be minus, okay, Fk is mu k mg cosine theta times the distance L is H over sine theta. All right. So this is what you have for this guy. This is work done by non-conservative force. Okay, your left-hand side equation is this guy. All right. Now your right-hand side equation, there are four terms. You want to identify each of them individually. Now there's potential energy involved here, gravitational potential energy involved here. So you want to pick a ground level. So you can pick the at the bottom of the slope to be the ground level because that's the low point of the motion. All right. So then for Ui initial potential, then that's 0. Okay. And then Ki is just 1/2 mvi square. Okay. When she reaches the top over here, then K final is equal to 1/2 mv final square. U final is then mg h. Okay. So that's the final vertical position is h over the ground level. So mgh. Okay. So you have those four terms identified. Now you can set up the equation starting from there. So for this guy, it's minus mu k mg cosine theta times h over sine theta, which is basically that guy. Okay, so take that guy down here, then equals to k final, all right, 1/2 mv final square minus k initial, 1/2 mvi square. Okay, plus u final will be mgh minus u initial 0. All right. So for the 0, you can just ignore that because it's 0. All right. Now you can take a look on all the items remaining here. So this guy, this guy, this guy, this guy. Okay, you can figure that there's m on each of these terms. So m can cancel out. Okay. So you actually don't need m. Okay, if you realize that. All right. So yeah, looking for this final, right? The final speed. Now there's a 1/2 in front of the square. You can probably multiply each of the terms remaining with 2 to get rid of 1/2. So then on this side becomes minus 2 mu k m mu kg cosine theta h over sine theta. Okay, equals to, you multiply by 2, so that get rid of the 1/2. And then also the 1/2 here. now plus 2GH. Okay. Now you are looking for this guy, the UF. You want to isolate the UF or VF, the final speed. Okay, so basically you can move these two terms to the other side of the equation. Okay, so then minus becomes positive, positive becomes minus. So it will become VI square minus twice GH minus 2 GH, right? So we can put GH first. There's G, there's H, there's mu K now. All right. Now, take a look on this guy here, the cosine over sine, that will give you cotangent, right? So you can put cotangent theta instead of writing cosine over sine, okay? That's equal to V final score, all right? So then to solve for V final score, you will just take square root of both sides of the equation, all right? So after that, you can plug in your numbers. For V initial is 12.0 meters per second square minus, okay, 2GH and then 2GH. You can actually single out the 2GH. So 2 times G times H, 2.5 meters, okay? And then will be, so the first term, because the 2GH is single it out, so it becomes 1, right, plus. So 1 plus mu K cotangent. Mu K is the 0.0800 and then times cotangent of the 35 degrees, okay? So this comes as the second line over here. All right, and then square root of everything, that will give you your V final, okay? It's a bit lengthy here, but you should be, if you are careful enough, you can solve all this, okay? So at the end, this is going to be, it turns out to be 9.46 meters per second, okay? For the final speed, okay? Questions you guys might have? Let me pause for a few seconds over here. All right, and I believe I saw a correct answer in the response, so that's good, okay? All right, so if you guys are clear, we will move on to the next slide over here. So if you have a track like this, two rail track, and then if you roll a ball down the track over here, now if the friction here is small enough, then what you will see is the ball is going to be rolling down, touching the valley here, and then goes up, and then rolls down, and then goes up until it reaches the point where it's the same level as it was released, okay? And then it will turn direction and then just going back and forth if the friction is negligible or very small, all right? Now in reality, there's a small friction. So then eventually this ball will stay either at point C or point B, okay? Because the friction will reduce the total energy, all right? So then at the end, the kinetic energy will be all dissipated by the friction force. But in this track over here, if you represent the energy at each point, that is combination of potential energy and kinetic energy, okay? So then you can plot the total energy versus the X. So it will look like very similar to the shape of the track, okay? So basically, the Y position will determine the potential energy of the ball, okay? And then the initial potential, initial total energy is going to be just the potential energy because initial kinetic energy is zero as is at rest. Okay, so then this is the total energy level. So then this will be the kinetic energies. Okay, above the curve over here until this dashed line, that will be the kinetic energy. All right, but kinetic energy plus potential energy at any point will be equal to this constant line. Okay, and then these 2 points, the velocity of the ball will turn direction. So those are called the turning points. Okay, for the motion if you release it. If you make a plot like this, the energy versus the x, the position, it's called potential energy, or it's called an energy curve. Okay, and then if you are looking at the gravitational potential energy here, then this is the gravitational potential energy curve. Okay, and then this, if they are at the same height, then it's called equal potentials because the height will determine the potential, gravitational potential energy. Okay. Now also, if you are reading a contour map of this, like this, it actually is the indication of the height of this mountain on the top view. Okay, so then a contour map, the lines here, although they indicates the height at a particular point, but it's also the equal potential lines. Okay, now, when you have contour map like this, then when you have the lines are closer to each other, that indicate it's going to be the slope over there is steep. So it's like this over here. Okay, the side view of mountain, you can see that when the side is very deep, the slope is steep, then the curves are close to each other. On the other hand, if you are looking at the this not so steep slope over here, then you'll see lines are more separated from each other. Okay, so that's the contour map. Also, they are the equal potential lines. All right. Similarly, if you are looking at the elastic potential energy, you can also plot elastic potential energy versus position. So then this is the elastic potential energy curve. Okay, for a spring system, it's going to be a parabola like that. Okay. And then also when at the high potential energy, the highest potential energy points, they are also turning points as well as the object will turn, the velocity will turn directions. Okay. Um, the next week you guys will be doing the lab of conservation of energy. So let me just give you a heads up here. Um, so what you'll be doing is similar to what you do this week for a simple pendulum. We are going to use a simple pendulum system. So you are going to pull it to a certain height, delta H, compared to the low point, where at that point you will have maximum potential energy. Okay, and then you're going to release it. You're going to record the height, and then calculate what's the potential energy maximum, and then let it go. So when it swings at the low point for potential energy, it actually has the kinetic energy maximum. All right. So then we'll measure the velocity at the low point, and then we are going to calculate the maximum kinetic energy. So the two energy maximum should equal to each other. That means potential energy at the high point, it's going to be equal to the kinetic energy at the low point. Okay, so that's what we will be doing next week. Okay. All right. The next section in the textbook mentioned about conservation of energy. So basically, it says the total energy is constant in any process. So that means if you have a process, the initial status, if you do all the energy combined, should be equal to the final status of the energy combined. Okay, so that's more universal law of conservation of energy. So it might include work done by non-conservative force and then all other forms of energy. Okay, then it should turn into the other energies. So for example, for a common case for non-conservative force is the friction force. So when friction force, work done by friction force actually will be converted into the thermal energy because friction at work usually produces heat. So if in the winter you are rubbing your hands when it's cold, then your hands becomes warm, right? So you actually, the friction force actually does the work, and then that converts to the thermal energy. All right. Now put this in another word: energy cannot be created or be destroyed. It will simply become a different format. Okay. So for example, mechanical energy may turn into thermal energy, or chemical energy may turn into thermal energy, etc. Okay. But the total energy for the universe is not, cannot be created or cannot be destroyed. So then that raises an interesting question about Big Bang theory. Okay, so the Big Bang theory predicted, or kind of proposed that our universe was born by a big bang when the big explosion at the beginning. But then that will violate this universal law of energy conservation, because in that theory it says that all the energy coming out was created at that point, right? So which is not exactly valid, all right? I think the success of the Big Bang theory is it actually explains what happens after the universe was created, but it doesn't explain how possibly it was created. Okay, so in that sense, that makes me like my faith stronger in the creation written in the Bible. Okay, all right, so I think that's how much I wanted to talk about conservation of energy here. We'll move on to the next section here in this chapter. So it talks about the power. So power is being defined as the measure of the rate at which work is done. So it simply is the work done during the time period T. Okay, so work divided by T will give you power. Now this is a new quantity, so we will talk about its SI unit. Its SI unit comes from the unit from the work and then the time. So it's joule over second. It also has its own name called watt or W. Okay, and then another. So that's SI unit. It's watt. So any another unit that you might hear a lot is the horsepower. 1 horsepower is equal to 746 watts. Okay, so that's the conversion there. So um, if you have an object that is moving at a constant speed, okay, so um, so that probably involves the friction force, gravitational air resistance force, and so on and so forth. Okay, because for constant speed, the object will have no net force on it. So then you probably will encounter several forces that cancel out each other. Okay, so when that happens, when the object is moving at a constant speed, then the power can be written as, because P is equal to work is equal to F times D, right? So we'll just assuming this is a one-dimensional, and then F and D are in the same direction. All right, so that gives you W divided by T. Now, D divided by T, it's actually the velocity, the speed, right? So you can rewritten the power as F times V, okay? So this is another way of calculating the power. So if you know the force, the driving force F, and then you know the speed of the object, then it's equal to driving force times the speed. Okay, T is equal to F also times V. It's defined as W divided by T, but it can be also written F times V. Okay. Now let's take a look on this example here. It says calculate the power output needed for a 950 kilogram car to climb a 2.0 degree slope at a constant speed of 30.0 meters per second, while it encounters wind resistance and friction totaling 600 newtons. Okay, so let me get you guys started with the a sketch over here. So assuming this is the slope, of course, this angle is more than 2 degrees, but this might be giving you a better um, visual on this. So the car is climbing up. Okay. Here, it has a speed of equal to 30.0 meters per second. Okay. Now, as I mentioned, usually it's important to indicate the free body diagram of the object of your interest. So then the mg goes down here, the normal force go there. All right. And then it says there's wind and friction totaling of 600. So let me just call this small f. Okay. Now, because this is moving at constant speed, so there must be a driving force, right, to balance out this resistance force and then part of the weight. Okay, so this is your driving force, Fd, F sub d. You can resolve your weight into its x and y component. All right, so that's what you are going to do. So then the y component again is mg cosine, the x component is mg sine theta. Okay. Then you're looking for what's the work, right? So in this case, you probably want to figure out what's the driving force from the free body diagram, and then use the equation of work equal to force times the speed. Okay, so I'll have you guys try to do this. Again, I think it will be appropriate for you guys to work on the as groups. Okay, so I'm going to open the breakout rooms again for you guys to work, and then we can take a look on the solution together in a few minutes. Okay. All right, so you guys are all back. We can take a look at the solution together, okay? I see someone has submitted the response. If you want it, you can still submit your responses there, okay? So as I mentioned here, you can do it this way. You can do the force times the driving force times the speed to calculate your power. I'm sorry, I shouldn't use W. That stands for work. So P for power, okay? So then looking at the free body diagram over here, you resolve the weight into X and Y components. So then because this is constant force, that means X component net force is equal to 0, Y component the net force is equal to 0, okay? So in X direction, net force is equal to 0. That means this driving force to the positive direction minus the friction, the resistance force, and then minus the mg sine theta, that should equal to 0, okay? So from here, you can write that your driving force is going to be equal to this resistance force plus the mg sine theta, okay? So I think it tells you the resistance force, which is 600 newtons, and then it tells you the mass of the car, 950 kilograms. The g is 9.8 meters per second square. The angle is 2 degrees, okay? So then you can calculate for your driving force, and your driving force multiplied by the speed should be just the power that you needed, okay? So you don't have to look into the other component, the net force in y component equal to 0, okay? You're not using that component. So it's basically 600 plus 950 times 9.8 times sine 2 degrees, okay? And then multiply by the 30 meters per second. That gives you the power. So it will be 27,747 in watts, okay? Roughly, you can write into scientific notation 2.77 times 10 to the fourth watts, okay? If you want, you can also express this in horsepower. So basically, this divided by 746, that will give you in horsepower, okay? Um, any questions you guys might have on that? I should mention, let me see. So it says yx is equal to 0. You mean the net force in x direction is equal to 0, right? Yeah. So it's because the it says has a constant speed, right? So constant speed, that means constant velocity. If you have constant velocity, then your net force should be equal to 0. Okay. Speed is not changing, that means no acceleration. No acceleration means no net force. So if you have no net force, then x direction net force should be equal to 0. Also, y direction net force should be equal to 0. Okay. All right. So if that answers your question, we'll move on to the last section of this chapter. Talks about world energy use. Okay, so from this pie, you can see that energy that we use around the globe comes from different sources. So the first three sources here, petroleum, coal, oil, dry natural gas, they are not renewable energies. Okay, but you can see those add up to be more than 85% of energy we are using. All right. Now the rest, they are renewable energy, electricity, nuclear electricity. Okay, and then also geothermal, wind, solar, etc. Those are small fractions there. So this we call green energy because they don't have carbon emission at all. So they are less than 50%. Okay. So still the majority of the power sources are um, non-eco, like environmentally friendly or non-renewable. And we have seen the increase of energy use over the years for the past 3 decades. And then these are the prediction for the next 15 years or so. So you can see increase usage for the energy. Okay. Also, the table here tells you about like for the countries, like the some major countries around the globe for right now, the usage for the energy. So you can see for the consumption wise, okay, so we are pretty much like the top usage of the energy. So we are using like 105 compared to the rest of the world. They are all less than 105 in the 10 to the 18 joules. Okay. And if you look at, so this is total usage for the country. If you look at for the per capita, so we are still number one here. Okay, so that means keep this in mind. We want to conserve our energy because most of energies are non-renewable. So so my advice to you guys is if you are the last to leave the classroom, turn off the lights, okay? So just do something that we can do to preserve the energy consumption, all right? All right, and that will finish this chapter. So I will stop here for today and then see you guys in class again on Monday online, okay?